Hello, my name is Alexander Swurzel, and today I'm going to present our paper Fully Dynamic K-Center Clustering in Low-Dimensional Metrics. This is joint work with Graham Scoracci, Monika Hensinger, Darius Leniowski, and Christian Schulz. So first to the static problem description. We will first define the K-Center problem. In the K-Center problem, you're given a set of points M, which is equipped with a distance metric d and an integer k greater than 0. The goal is to find a set of centers C, which is a subset of M, which minimizes the maximum distance from any point to a center, such that the size of the set of centers is equal or smaller than k. Okay. So, and in this example, we're given houses and we want to place fire stations, and so that's like a toy application, and obviously each house needs to be reached by a fire station very quickly. In the dynamic problem description, the set M of points of houses evolves over time, and at each time point t, you will either insert a point, remove a point, or query a center of a given point. And in the naive solution, you could recompute everything from scratch and use your algorithm for the static problem. But of course, we hope to find something better. And in this setting, the running time is measured per update. So it's the time you need at each time step to process the update. Okay, some further definitions. So dmin is the smallest pairwise distance between 2 points in M. Dmax is the largest pairwise distance of points in M. The aspect ratio delta is dmax over dmin, and a ball Bxr is defined as the set of points in M where the distance between the point and x is smaller or equal than r. And now to another definition, doubling dimension. So we say that a metric space, the doubling dimension of a metric space is bounded by kappa greater or equal than 0 if any ball Bxr in MD can be covered by 2 to the kappa balls of half the radius. So for example, the doubling dimension of a line is 1 because this ball can be covered by 2 to the 2 to the 1 balls, so 2 balls, 2 to the kappa equals 1, to the 1 balls of half the radius. As you can see, each of the points on the line is covered by those 2 balls. And also an interesting fact is one can show that RD has doubling dimension of theta of D. Previous results for the K-center problem and also the static and the dynamic K-center problem are as follows. So we have Gonzalez 85, which yields 2 approximation in the static time, so running time n times k. This holds for any metric space, and then Feder and Green and Harpilet, Mendel in 88 and 06 found some other algorithms for the static setting where in the first case you were restricted to RD, and in the second case to metrics with bounded doubling dimension. And then you obtain n log n and n log k. And okay, so now to the dynamic, partially dynamic setting. So in the insertion only setting, you would have an update time. So Charika et al. In 97 got an algorithm with 8 plus epsilon approximation with k log k update time, but this supported insertion only. Later on, McCutcheon and Kaller improved this, also insertion only, to a 2 plus epsilon approximation, but they pay epsilon to the -1 log epsilon to the -1 additional running time per update. Then there is another setting which is called sliding window, where a point is inserted at some time point t and removed at time point t plus w, where w is the window size. And Ko and Haddad in 2000 and others in 2016 found an algorithm with approximation 6 plus epsilon, and the update time was k squared epsilon to the -1 log delta. Also, delta is the aspect ratio, that's the typo. This is a randomized algorithm, and yeah, so that's its restriction, and it only works in the sliding window model. And then later on, Harpelet in 2000, so not later on, this was actually before, but this is an implicit result. They obtained in 2004 already a fully dynamic result with 2 plus epsilon, where the update time is some polynomial in k epsilon to the -1 and log n, but they do not specify the polynomial in the paper. I just mentioned that they obtained this result. And the restriction here is that it's only working in RD. And recently, this was the paper that inspired us to get working in this topic. Chan and others in 2018 obtained a 2 plus epsilon fully dynamic algorithm, works for any metric space, and update time is k squared epsilon to the -1 log delta. So delta is the aspect ratio, and this is fully dynamic. And so, independent of our work, Schmidt and Solar got 16 approximation, update time log squared delta log n. This is fully dynamic also, but randomized. But they were looking actually, so this 16 may seem bad, but they were looking at another problem, and this result is just implied by their result. And so to the negative results, finding a 2 minus epsilon approximation is NP hard. This was shown by Gonzalez in 85. Finding a smaller than 1.732 approximation for Euclidean spaces is also NP hard. This was Feller and Green 88. Okay. So now, as you can see, all of these results, they have k or something worse in the running time, except for Schmidt and Solar, which was independent of our work. And we asked the question, so this is the main, so question 1, are they fully dynamic, deterministic, because many algorithms were also randomized, for the k-center clustering problem with a running time independent of k, while guaranteeing a 2 plus epsilon approximation ratio. And the second question we had was, can we achieve a speed up compared to the state-of-the-art dynamic k-center algorithms in benchmark instances with this new algorithm? And we answered the first question in the affirmative. We found an algorithm for the fully dynamic k-center problem with approximately 2 plus epsilon and O of 2 over epsilon to the O of kappa, where kappa is the doubling dimension, not k. Log delta times log delta times ln of epsilon to the -1. And yeah, kappa is the doubling dimension. And for the second question, we compared with the state-of-the-art implementation. So this is Chan and others in 2018. And we obtain an advantage in running time and solution quality for large values of k. And for epsilon greater than 0.5, we obtain better solution quality. And also when we want to sacrifice 25% solution quality, we are orders of magnitude faster, but more of that later on. Okay, so for the technical overview, for the ingredients for the theoretical result are as follows. So the first ingredient are RNets. They were already used for approximation algorithms for the static k-center clustering problem by Harpelet in 2011. It's a book. Navigating nets. This builds on RNets, and it's a data structure for proximity search. This was Krautgamma and Lee, 2004, they invented this data structure. And this data structure, and that's the nice thing, supports insertions and deletions out of the box. And yeah, you can obtain a fully dynamic 8 approximation with this navigating net data structure. And our contribution was to improve this to a 2 plus epsilon approximation with a technique which was initially invented for streaming algorithms by McCutcheon and Kallert 2008. So this was this incremental thing. Yeah. Okay, so let's dive right into it. RNets. So an RNet is defined as follows. So you're given some metric space MD and an integer r greater or equal than 0, and the RNet YR is a set of points which we call centers with the following two properties. Okay, so the first property is the covering property, which says that every point in M is in some ball um, YR for some Y in YR. So basically what it says is, if you look at this example, if you look at Y2, then every guy in M has some guy in Y2 with distance less than or equal to 2. So with distance 2 you can reach some guy in Y2. That's the covering property. And the second property is called the separating property, which says that distinct points y and y prime in YR have distance at least r. So in our example, the points in Y2 are at least 2 apart from each other. And notice that if the size of YR is less than or equal than k, then this is a good basis for a k-center solution. This was also what Harpilet showed in this book, because it covers every guy in M, and also because of the separating property, there cannot be many centers, and so it's a good evenly distribution. Okay, and so now let's move on to navigating nets. So navigating nets are more general, and so a navigating net has a set of scales which is defined as alpha to the I, for where I is an integer and alpha is greater than 1. For example, you can, in this example we set alpha to 2, and then you do what you do is you define an RNet for all scales. So for each R in gamma, you say if the R is smaller or equal than the minimum distance in this in M, the pairwise minimum distance, you define the YR to be M. You need every point to be an RNet, and then you use this RNet definition recursively. So if for R is greater than dmin, you define YR to be an RNet of YR over alpha. So for example, this Y2 to the 2 is an RNet of Y2 to the 1. And then you do this until you only have one point, basically. And a navigating net formally is then defined as the union over all of these YR for R in gamma. So all of these sets are, the union is this navigating net. Okay, and you can show that you instantly obtain an 8 approximation using this navigating nets. And how do you obtain the solution? You construct the navigating net with alpha equals 2, so the same thing we did here. And then you consider the deepest level, y to r, of the tree with less than or equal k centers. So if k is free, you would output this level as your solution. And now the nice thing is that navigating nets also support out-of-the-box insertions and deletions, and so you can use this to maintain a fully dynamic k-center solution. And yeah, you can show that the solution that you output here is always only 8 times worse than the optimum solution. Okay, so just to assert the point of this fully dynamic thing, I'm going to describe how to insert a point into the navigating net. So let's say you have some point Q comes in, and how do you update the navigating net? So I want to insert some new point, let's say 11. Okay, so what would I do? I would insert Q into the minimum level, because obviously the pairwise minimum level, you need to insert it, and then you consider the next level R, which is R times alpha. So in this case, R times 2, or 2. And then you insert Q when the distance between Q and this YR is greater than R. So basically, in this step, you're taking care of the separation property, so that everyone is still far apart. And if this is not the case, so if the distance between your new point and yr is smaller than r, you can terminate because someone covers this point already. So in this case, for 11 you would not have to insert the point because into y2 1 because 9 is already covering it. Okay. So yeah, of course this guarantees, you can show that this guarantees for all r in gamma that yr stays in rnet, and there is an efficient implementation of this algorithm because you can show that you can only you're able to consider only a small subset of each of the YRs, so which we call ZR, and we show in the paper that the size of this ZR is smaller or equal than 2 over epsilon to the O of kappa. And this is also where the doubling dimension plays its part. So it's not in the approximation factor. So the approximation factor always holds for all metric spaces, but the running time guarantee is only for metric spaces with bounded doubling dimension. And yeah, because the height of the tree is log delta, this was already shown by Krautkammer and Lee in the original paper, and you can implement each of the YR things with a binary with balanced search tree of height log delta. You insert it in time log delta, and so the insertion update time is the size of this set times the size of the tree and the insertion time. And so that's how we obtain the insertion, also the deletion time. For deletion you can do something similar, but you would also need to take care of the children and so on if they don't have a parent anymore, and it gets a bit more messy because you might have to move some children up some levels and so on, but it's still possible in the same running time. Okay, and so how do we obtain the 2 plus epsilon approximation? So instead of one tree, we maintain m. So instead of one navigating net, we maintain m navigating nets. And so before the set of scales was this gamma alpha to the I in the set of integers, and now with m navigating nets you would get gamma p. So for each of these navigating nets you have the set gamma p, which is defined as alpha to the I plus p over m, where m is this number of navigating nets and p is the current navigating net you're looking at, minus 1. And again, to extract a solution, you would, for each of the navigating nets, consider the deepest level with less than or equal than k centers, and then you, from all of those levels, you would pick the level which minimizes alpha to the I star p. Okay, because so alpha to the I star, which minimizes alpha to the I star, and I star is this exponent which is defined for each navigating net. And of course this increases the update time by a factor of m, so the number of navigating nets, and yeah, and so that's how we arrive at our running time. And yeah, and so the main theoretical result which we're able to show is that when we set m to this epsilon to the minus 1 ln epsilon to the minus 1 and alpha to 2 over epsilon, then we can show that this level we output always is always a 2 plus epsilon approximation. So basically that's the main theoretical result. The details you can find in the paper for this approximation guarantee, but note that this always holds. So we don't need a bounded doubling dimension or something. This only affects the running time. Okay. So now let's talk about the implementation. So what we did is we implemented this algorithm, but instead of using navigating nets, we used cover trees. This was described by Begelsimer and all. It's a follow-up work of this navigating nets data structure, and it's a practical variation. So it's a fast practical implementation of this navigating nets data structure. And their key difference is that they store only one point, one level up, and also that now they have an expansion constant instead of doubling dimension in the running time. And this expansion constant is defined such that the size of each ball with radius 2r is smaller or equal than c times the size of the ball with half the radius for all points in M. So, and this c is defined as such. Yeah. And note also that this is no faster theoretical result because c is not bounded by theta of d. So it could also be 2 to the d. Yeah. And yeah, the state-of-the-art algorithm for comparison is the algorithm by Chan, ACGS. And what they do is they maintain k-centers for different radii. So and this set is defined of radii is defined as 1 plus epsilon to the I, and between d min and d max obviously, and their update time is k squared log delta over epsilon. And one thing I want to mention is that they need d min and d max as input parameters, which we do not, but we pre-compute their input, so the input parameter for them initially, and we don't add this to the running time. Yeah. So how do we do the experiment? We do 10 runs per instance, and for each of them use arithmetic mean, and for multiple instances to weigh them correctly, we use geometric mean. And when we measure solution quality at some time point, we query the set of centers Ci. So this we count for the running time, and then we compute the maximum. So then we compute the objective function. So we really compute the k-center value, but we do not count the running time for this because, yeah, it's the same for both algorithms, and it's not you wouldn't do this in practice. So yeah. Instances we used were Twitter, so this is geotag, tweets, Flickr, this is metadata from pitches. Both of those instances were also used by Chan et al. And then we also put something new, which is random, where we sampled some centers, and then for each of the centers we sampled more points. In all our instances we use Euclidean distance, and for this dynamic evolving of M, we put the following. So we did two settings. The first one was random insertion and deletion, so 30% deletions, 10% deletions, 5% deletions, and sliding window, where we insert a point at time t and remove at time t plus w, where w is the window size. Okay, so now the results. The top describe of this table describes the geometric mean speedup of ACUF over ACGS, so our algorithm over theirs, and the bottom is the geometric mean improvement in solution quality of our algorithm over theirs. And so, as you can see, when k equals 200, so as k goes up, our solution quality improves, our speedups improve, and yeah, as you can see, for 200 we are always when we put 200, we are always faster, at least 1.15 times. So this is for epsilon 0.1. Yeah, and because they have a better trade-off with this epsilon, the same holds for the epsilons. And yeah, you can see solution quality is about the same, but interestingly, if epsilon is greater or equal than 0.5, we are always at least 7% better. So this here is the only thing with 7, but it's actually about 10% mostly better. And that's why we came up with the idea of actually fixing the epsilon to 1 and 4 for our algorithm and compare with their best results. And so there, the results already look a bit more interesting. So in this slide, basically, when we fix our epsilon to 1, we sacrifice about 10%, I would say, in solution quality. But so we are already, for even k equals 20, we are already 2.5 times faster, and k equals 50, 10 times faster, k equals 100, 32 times faster, and then already 130 times faster. And if we fix epsilon to 4 for our algorithm and compare with their 0.1, epsilon 0.1, we sacrifice, I would say, about 25% of solution quality, and but we are orders of magnitudes faster. For k equals 20, 12 times faster, k equals 50, about 50%, 50 times faster, 100, 159 times faster, and for k equals 200, we're 600 times faster. So yeah, so that's interesting. Yeah, thank you for your attention.